This is what a massive distributed system looks like when it collapses under its own unoptimized weight. Hadoop is the foundational architecture for managing and analyzing large datasets in distributed computing environments. It serves as the bedrock of enterprise big data processing. But there is a persistent misconception about how it works in production. Many assume that a cluster can scale infinitely simply by throwing more hardware at it. Welcome to Royal Research. Today, we are deconstructing common performance bottlenecks in Hadoop clusters to show why that hardware-first assumption fails. Cluster performance is governed by two core engines. First, the Hadoop Distributed File System, or HDFS, which manages storage. Second, Yarn and MapReduce, which manage compute resources and task scheduling. True scalability relies on targeted software tuning and dynamic resource management across these specific engines, rather than raw physical expansion. We start at the HDFS layer. The baseline architecture here consists of the name node, which acts as the master directory, and data nodes, which function as the storage workers. By default, Hadoop chunks incoming data into 128 megabyte blocks and distributes them across the file system. Managing millions of default blocks causes the name node's memory to hit maximum capacity. Consolidating tiny pieces into larger block sizes drops this metadata overhead. However, smaller blocks distribute compute load widely, which is preferred if your workload prioritizes parallel processing speed. The replication factor dictates data redundancy. The default setting is to copy every piece of data 3 times. In non-critical environments, lowering this replication factor reclaims massive amounts of physical storage space. It also directly improves write performance. Generating fewer copies means less network I/O is required to move that data around the cluster. Supporting this with proper disk configurations, like utilizing high-throughput disks and specific RAID arrays, prevents silent hardware degradation from compounding the I/O load. HDFS storage tuning requires balancing the strict memory limits of the name node against the latency requirements of parallel processing. Even with optimized storage, data still needs to move. This introduces physical network bottlenecks across server racks. If a data block is on rack A, but its assigned node manager is on rack B, the packet gets bottlenecked at the switch. Data locality generates the lightweight compute task directly on rack A, entirely eliminating the heavy data transfer across the network. To enforce this, administrators must explicitly enable a configuration parameter called rack awareness. Rack awareness forces the resource manager to map the exact physical locations of all HDFS blocks. It then deliberately assigns node managers located on those specific racks to process them. This configuration inherently improves fault tolerance. It ensures data replicas are never stored on nodes sharing the same physical power source or network switch. Network hardware cannot outpace physics. Software configurations must be set to prevent heavy data from traversing the network in the first place. Zooming into the compute layer, we evaluate the individual node managers executing these tasks. Both name node and data node processes operate within strict Java heap memory limits. If this heap allocation is insufficient for the workload, it triggers a frequent garbage collection cycle to free up space. These garbage collection pauses completely halt the node's operation while the memory clears, creating severe system-wide latency spikes. Yarn memory settings carry similar risks when left static. Static allocation causes some containers to starve for memory, while others remain completely idle. A rigid static grid leaves empty gaps where varying size tasks fit poorly. With dynamic resource allocation, container borders smoothly adjust. The system instantly reallocates space for a massive high-priority task without dropping the smaller ones. The final compute bottleneck is the straggler task, a single slow-running process that delays the completion of an entire job. To safeguard against this latency, administrators enable speculative execution. A duplicate task spins up in parallel, racing ahead of the struggling original. The system uses the output from whichever finishes first, guaranteeing optimal completion time and immediately terminating the original slow task. Compute optimization requires abandoning rigid static setups. A system must be flexible enough to dynamically manage its own memory and neutralize stragglers automatically. Stepping back to a macro view, we now observe a cluster running seamlessly with all tuning parameters actively applied. Hadoop efficiency relies on 3 pillars: tailored HDFS storage configurations, strict network data locality, and dynamic yarn scheduling. Maintaining this high-performance baseline as data volume grows requires ongoing operational discipline. Administrators must implement efficient data partitioning. This ensures blocks remain evenly distributed across all nodes, preventing isolated processing bottlenecks. They also utilize incremental data processing to handle system updates. This prevents the cluster from having to recompute massive legacy datasets from scratch every time data changes. Supporting this with data compression algorithms speeds up internal transfers, while maintaining strict version control guarantees all components stay perfectly synced. Out-of-the-box defaults are merely a starting point for your system. Robust linear scalability is achieved strictly through deliberate, engineered configurations. For further insights into advanced data engineering architectures and performance scaling, visit us at Royal Research.